everybody. I'm here to present the first two questions on the group assignment from this week. The big part of this project was creating a spreadsheet that would model what would happen with the different parameters put in for quarantine rate and for transmission rates. And so I'm going to walk through and talk about how I set up the spreadsheet for the first one, and then I'll go through the answers for the first question and the second question both. So anyway, the spreadsheet, it looks like this. We were interested in what would happen over the 6 days, basically. The first 3 days being non-symptomatic and non-contagious for the 4 days, and then for the fourth, fifth, and sixth day, the infected students were symptomatic, but only contagious on the fifth day and the sixth day. And then after the sixth day, they recovered and kind of fell out of the system. So we started out with 16 students on day one. So this is just, I want you to kind of focus on the FX up here is, I just put in 16 students, and then, so of course this was the very first day. There was nobody that was beyond the first day of the having the disease. So the first line was pretty easy to fill in. And then we wanted to think about what's going to happen on the second day. So on the second day, all those students that were infected on the first day now are day 2 infected, and so this number 16 is just going to slide over to the next column. So the value in this cell ends up just being equal to the value that was up and to the left of it. And then the same thing was going to happen here. Had there been anybody who was day 2 sick, would slide over to day 3. And then on day 4, same thing would happen. Anybody who was sick on day 3 is now sick on day 4 on the fourth day. And then again, going over here to the contagious part then, I guess I missed one here. These were going to be just zeros up here, but what happens then on the day that they're symptomatic is anybody who was sick and is symptomatic on the fourth day, half of them are going to stay home. So this value ends up being half of the value that's up and to the left of it, because of these 16 kids, half of them are going to stay home according to this. I initially set this spreadsheet up by using 1/2 in here instead of a formula. And then there's this round up command. We were supposed to round this up to the nearest integer. And then I realized that we're going to have to adjust this quarantine rate for different problems. So I thought it would be beneficial if we had a cell that we could put in the quarantine rate. And so if the quarantine rate was 50%, we could just take 1 minus 50%. We actually get 50% on this one. Multiply that by the number of students that were day 3 sick, and we would end up getting that value that then could be adjusted just by changing the quarantine rate. And then this one, again, the students that were 4 days sick, half of them were going to stay home. This is basically the same formula. And then on day 6, half of those students that were day 5 ill would then be quarantined. All right, and then going back over here to the first column then, what happens in the next 6 days is that the students that are here are possibly going to be first day infected. Okay, and what happens is we take the number of students over here that were sick and contagious, and we add them together, and then we multiply that by 1.5, because 1.5 was the number of expected people that they were going to pass the disease on to. So I figured that it might be beneficial, again, if we know what that transmission rate is going to change, we could put that into the formula. So the J3 up here in the formula is the transmission rate. F8 and G8 are the sum of the two types of people that were contagious the day before, and then divide that by 2 because they were contagious over 2 days, and we end up getting the value that's here in cell 6. Cell B9. All right, and then once we got those cells put together, all I did is I copied the formulas here and filled them down. I guess there is one more column here that is the total number of infected people is just the sum of the different kinds of infected people, and this is the number that we're kind of interested in seeing what happens over time. All right, so when I put in the 50% here, and I put in 3 for the transmission rate, we see that the number of infected stays constant at 16 because, well, these guys didn't pass the disease on anybody yet. And then once we get to the 4th day, we see that number start to vary a little bit. It does kind of go up and down for a while, but then the tendency is that it's going to die out. And just as soon as we get 0 people that have the disease, obviously it's not going to spread anymore. Okay, the other thing I thought would be kind of interesting is if we could kind of track these with a graphical display. So I just went down and I copied about like 30 of these and said, let's insert a graph. And the kind of graph I wanted to look at was a scatter plot. And so this is a graph of the number of infected people as a function of the number of days that have passed. And you can see that on the 16th day, that's when the disease died out. All right, and we can see that that happens in this table on the 16th day. Okay, so once I got this problem done, then moving on to question number 2 was a very simple task of just changing this number to 0.25. We were going to decrease the quarantine rate to 25%, and when I put in a new value there, it updates all the values in this column, and then graphically you can see that the general trend was for this number of infected people to increase. The general trend is to increase. I think if you look at it at a small scale, you see that it's kind of almost periodic, but that's periodic because there's those 2 days in there where you end up with people kind of rolling through those 2 days that are infecting more people and so on. But you really need to look at the general trend on this. I also thought it might be beneficial to look at what happens maybe over a longer period of time. And so if I change the data here, I know that this goes up to column or row 303 is what I have set up. And you can then kind of see the general trend that, you know, after a while, this thing is just going to blow up. And so I think here you see a little bit better trend of what happens over time. If we feel like we don't need to see that much data, we could just do this for like 100 days and see. Again, you see a little bit of variability here, but the general trend is that the number of people that are infected is going to keep going up. So this does have some kind of an exponential nature to it. The one thing that I don't think we addressed in this problem was, can people be infected a second time? And we're kind of assuming here that we've got an infinitely large population, so there's nothing to slow it down, I guess. I know that in actual studies that if there's a disease that once you get it, you can't get it again, then that's going to slow down the transmission rate because there are fewer people that are available to contract it initially, and you end up with something that looks a little bit more like a logistic curve where it levels off at some value. A lot of times that ends up being 100% of the population. All right, well, I hope this is helpful. I know that our group found it helpful to have these 2 cells in here where we could adjust and make different conjectures. And I think Tara, she discovered something that was kind of interesting on question number 3, so you want to make sure that you watch that one. That some of us didn't get it because we didn't carry this out far enough to see what might have happened, but she'll explain that in her video. Okay, all right, thanks for watching. Bye.